In this video, we want to study the last section of chapter 4, and it is about the metallic bond. At the end of this section, you must be able to explain electrical conductivity and malleability and ductility in the metals, and also you must be able to explain trends in the melting point of the metals. If you look at the periodic table, you can see that the most of the elements in the periodic table are metals, and they are located at the right side of the periodic table. So they have low ionization energy. You know that ionization energy increases when you are going to the right in the periodic table. So the elements at the left side, which are metals, especially the S group metal, they have low ionization energy. That's why they can easily lose their electrons and form the ionic compound. But if there is no other atom to form the ionic compound, these electrons can move throughout the structure of the metals from one atom to another atom. So that's why in the metallic compound we have delocalized electron. So the valence electrons in the metals are delocalized and they don't belong to any specific atom, but instead they can spread themselves through the metal structure and they can move from one atom to another atom. Move to the next page. This is the picture of a model of the metal that we have. When the metal atom loses its electron and its electron move to the orbital of the adjacent atom, the metal atom becomes positive. So in the metallic material, you have positive ion of the metals which are surrounded by these delocalized electrons. These delocalized electrons are usually called pool of delocalized electron or sea of electrons. So it says in metals there is a force of electrostatic attraction between the lattice of the cations and delocalized electrons, and this is known as the metallic bond. So in the metals you have a delocalized electrons here, and the metal ions are inside these delocalized electron or sea of the electron. The charge of these delocalized electrons are negative because you know that the charge of the electrons are negative and you have the positive ions inside the lattice structure of the metal. There is a strong attraction between these delocalized electrons and positive ions, which we call it metallic bond. The strength of the metallic bond determined by three factors. The first two are related to each other, so the number of delocalized electrons and the charge on the cations. Okay, so if the metal has one valence electron, like the group 1 metals, they lose one electron per atom, and the charge of the cation would be positive 1. If the metal atom has two valence electron, like group 2 metals, they lose two delocalized electron, or they have two delocalized electron per atom, and the charge would be positive 2 or 2 plus. So the number of the valence electron determines the number of delocalized electron per atom and also the charge that would be on the metal cation. And the third thing that determines the strength of the metallic bond is the radius of the cation. If the cation becomes smaller, here you can see that the distance between the metal ion and sea of electron decreases, so the electrostatic attraction increases. We can show it here that if the metal is big, like this one, suppose it has two valence electrons, so each atom will have two delocalized electrons. So there are two delocalized electrons per atom in the lattice structure of the metal, and the charge of the cations would be 2 plus. Suppose you have another metal exactly with the same number of valence electrons. So that metal also gives 2 delocalized electrons per atom to the lattice structure, and the charge of the cation would be 2 plus as well. But this metal is smaller than the previous one. So what happened in this case? In this case, the distance between these delocalized electrons that you have here and the metal atom is smaller, so the electrostatic attraction increases and the strength of the metallic bond is bigger here compared to the same charge of the metal with the same number of the delocalized electron but the bigger metal ion. Okay, and as we just said, another factor that determines the strength of the metallic bond is the number of the delocalized electron that you have and the charge of the metal. Suppose you have two approximately metal with the same radius, but this blue metal only has one delocalized electron per atom. So the charge of the metal ion would be positive 1, and also the negative charge of the C of electron would be smaller than negative charge of C of electron, for this case the black one. So that's why in this case, which you have less delocalized electron and the charge of the metal ion is smaller, the metallic bond would be weaker. Let's go back to the periodic table and see how or what is the trend of the metallic strength when we are going from the left to the right in the periodic table. So the sodium has one valence electron. So each atom of the sodium gives one electron to the metallic lattice, and the charge of the metal would be positive 1. For the magnesium, each magnesium atom has two valence electrons, so there would be two delocalized electrons per magnesium atom in the lattice structure of the metal, and the charge of the metal would be 2 plus. And for the aluminium, there are three valence electrons, so for each aluminium atom there are three delocalized electrons, and the charge of the metal ion would be 3 plus. So when you are going from the left to the right, because the number of the electron or number of delocalized electron increases and the charge of the nucleus increases as well, the metallic bond becomes stronger, so the melting point of the metal increases. It means aluminum has greater melting point than magnesium, and magnesium has higher melting point than sodium. Another thing that we have when we are going from the left to the right is that the radius of the cation decreases. This is another reason that tell us why aluminium has higher melting point than magnesium and magnesium higher than sodium, because their size becomes smaller. But when we are going down the group, for example, group 1, the number of delocalized electron per atom remains the same. Lithium has one valence electron, sodium has one valence electron, and all of the elements, metals in group 1, they have one valence electron. So they give one electron per atom to the C of electron, and the charge of the metal ion for all of these cases is positive 1, Li plus, Na plus, K plus, Rb plus. But the difference here is that when you are going down the group, the size of the metal ion become bigger. When the size of the metal ion become bigger, the metallic bond becomes weaker, so the melting point decreases when you are going down the group. This happens for all of the groups in the periodic table. For example, the group 2, when you are going down the group, the number of delocalized electrons remains same. Each atom gives 2 electrons to the C of electron. The charge of the metal ion is same, Mg2 plus, Ca2 plus, Sr2 plus, Ba2 plus. But because the metal ion becomes bigger, the metallic bond becomes weaker and the melting point decreases. So here in your book, the melting point for the sodium and magnesium is given. So you can see the sodium, which forms Na plus, has much less melting point than the magnesium, which forms 2 plus. So each magnesium atom have two delocalized electron, and each sodium atom there is only one delocalized electron for each sodium atom. So the number of delocalized electrons for sodium is less than magnesium, the charge of the metal is less than magnesium, and also because we are going from the left to the right, Mg2 plus is slightly smaller than Na plus. All of these three factors cause the metallic bond in the sodium to be weaker than Mg2 plus, so the sodium has less melting point and Mg2 plus has higher melting point. But when we are going down the group, like sodium, potassium, and rubidium, all of them has one delocalized electron per atom, and the charge of all of them are positive 1. But when you are going down the group, the size of the cation becomes bigger, so that's why the metallic bond becomes weaker and the melting point decreases. So melting point of sodium is 98, but for rubidium is 93. Transition elements, which are here in the middle of the periodic table, they have very high melting point and boiling point because they not only you lose their ns electron, but they also can lose n minus 1 d electrons because the energy level of d electrons are very close to the s orbital, and both of them can be delocalized. So they have a lot of negative charge in the sea of electron, and the charge of the cation is very big, which results in the high melting point. Okay, so let's move on. This table is very important. Based on this model which we have explained for the metal, different properties of the metals are mentioned, and at the same time the explanation for each one of them is given with their application. For example, the metals are good electrical conductivity. This is because of the delocalized electrons. They are highly mobile, so they can move through the metal structure when the voltage applied on the metal. That's why we can use them in electrical circuit like the copper. They are good thermal conductivity. There are two reasons of that. The first one is delocalized electron, and also the ions are packed to each other, so they can efficiently transfer the heat energy, the kinetic energy from one atom to another atom. Okay, and the application based on these properties is the cooking utensil. The metals are malleable, means they can make different shape from them, and they can bend without breaking, and they are ductile, means they can be drawn out into the wires. Both of these properties is because of the movement of this delocalized electron, which is non-directional. Okay, so look at this model which I have drawn here to you. Suppose you have a metal ion with positive 1, and for each atom you have one delocalized electron. Now suppose you exert the force here. What happened? These layers of the metal ion shift downward. As you can see here, they are shifted downward. But the delocalized electrons are not directional. It means they are not only can be in this direction. They move here and they are still around the metal cation even though they have changed their location. So that's why the metal ion doesn't break from here, or metal solid doesn't break from here, but they change the shape. Same thing happens when you pull the metal from two directions to make the wire. These metal ions slide past each other and delocalize electron around them and keep the metal ion together. The metals have high melting point. This is because of the strong attraction which are available between the metal ion and sea of electron. In other one, because of the strong metallic bonds which are available them, and it's not easy to separate the atom from each other. Because they have high melting point, they use it in the many material like the turbine engines. And tungsten is the metal which has highest melting point. The symbol for the tungsten is W. The metals are shiny and lustrous. This is because of these delocalized electron. They can reflect the light, so they use the metal in the ornamental structure for decoration. In the next topic, we want to talk about the alloys. Alloys are solution of the metals with enhanced properties. So we have solution of the metal, we have solid solution. When we talk about the solution, it means two material are mixed to each other and they are evenly distributed in each other. We can make the alloy from the metal by adding another metal or carbon to the metal when it is melted. So we melt two metal and we mix them when they are molten in the liquid format. When they solidify, they will make the alloy or solution of the metal. An example of solution of the metal is shown here. So here you have three type or two type of the metals are joined to each other. This is one, the green one, and the gray one. And you can see that the gray metals are evenly distributed in the in the yellow metal ions, and you have the sea of electron around them. So these delocalized electron keeps both of the metal ion in the crystal structure, and says the production of the alloy is possible because of the non-directional nature of the delocalized electrons and the fact that the lattice can accommodate ions of different size. So you can see here the two metal in the alloys doesn't have the same size. They don't have the same size. The yellow one is bigger and the gray one is smaller. So this definition of the alloy is important because alloys are solid solutions usually containing more than one metal and held together by the metallic bonding. So why we need to make the alloy from the metal? When we make the alloy, usually the properties of the metal enhances. Okay, so the metal becomes stronger, it becomes more chemically stable, and it becomes resistant to corrosion. So all of these shows that the properties of the metal has improved. On the next page, name of the several alloys are mentioned here. For example, steel is the mixture, homogeneous mixture or solution of the iron and carbon, and it is stronger than the iron metal, pure iron metal. But the problem that it has, it corrodes, it rusts. That's why they made stainless steel, which is the mixture of the iron and other elements like the nickel and chromium. This one is widely used in industrial appliances because of their strength, and also it is resistant to corrosion. The brass is the mixture of the copper and zinc, and they use it in the plumbing fittings. The bronze is the mixture of the copper and tin. In the coins, metals, tools, and heavy gears, they use the bronze. Pewter is the mixture of the tin, antimony, and copper, and they use it for the decorative objects. Duralumin is the mixture of aluminium, copper, and manganese. They use it in the aircraft and boat and different machinery due to the high strength and resistance to corrosion. Nichrome is the mixture of the nickel and copper. They use it in the heating elements in the toaster and electrical heater. Solder is a mixture of lead and tin. This mixture has low melting point, so they use it for joining two metals. And sterling silver is the mixture of the silver and copper. They use it in the jewelry. Okay, you don't need to memorize this table. This table is just for an example, so don't need to memorize this table. Now let's answer some question. Question number 31, 32, and 33. Question 31 says, which is the best definition of the metallic bonding? The answer is B, the attraction between the cations and delocalized electron. It's very important. In the metallic bond, you have delocalized electron. Question 32 says aluminum is widely used metal. What properties make it suitable for the following applications? Okay, they use the aluminum as a baking foil. The properties that make it suitable for baking foil is that aluminums are malleable, so the malleability. Also, because we are using for baking, its thermal conductivity is important, and its thermal stability is also important. It must be stable. If, for example, if you have a substance that by applying heat it combined with the other material is useless for cooking. And also it's insoluble, so it doesn't dissolve in the different materials that we use for cooking. In aircraft body, the main properties of the aluminum that we use it in aircraft body is it is light, and at the same time it's strong, and it can form alloys with different metal, and it also thermal stable, so it has thermal stability. Cooking pans, so because we are using for cooking, so the main properties of the aluminum that make it suitable for this one is that it is thermal conductive and also thermal stability and insolubility. For the tent frames, okay, we use it in the tent frames because it's light, strong, and non-corrosive. It doesn't rust easily. Question 33 says suggest two ways in which some properties of aluminium can be enhanced. So one of them is very obvious, making alloy. Okay, so alloying, mixing it with another metal to enhance its structure. For example, we can mix the aluminium with magnesium and copper to increase its hardness and strength. The next properties or the next way to enhance the properties of the aluminium is called anodizing. I explain what is anodizing here. Suppose this is the metal. This is aluminium metal. When the aluminium metal exposed to air, it reacts with oxygen in the air and it forms aluminium oxide, Al2O3. The aluminium oxide is very sticky and it attached to the surface of the aluminium. So on the surface of the aluminium in the air, very thin layer of aluminium oxide forms. This is called anodizing. Aluminium oxides are resistive to corrosion, and it also protects the rest of the metal from further oxidation. So it prevents aluminium from further rusting. So by these two ways, we can enhance the properties of metal.